start. Just so that I understand why. Here's the filter problem. Okay. I wonder if I can put a hat on this as well. Here's some. That seemed to work. Now there. Two noise suppressions. Okay. All right, so I never worked this problem, but this brings up an interesting point, and I'm going to try to work this. And after this, I'm going to go down. I'm going to work this one after that one. So I'll make a place for it. Okay. And I'll drop it right there. Let me go back and do this. So in all these problems, you've got concepts of continuity. You've got Bernoulli, which conservation of mass. Bernoulli's is conservation of energy. Now, momentum, and they really don't have a good name for this, but it's just conservation of momentum. Now, the physical laws of nature require this one to be met, and they require this one to be met. Now the way we've cast this Bernoulli's equation is we've made one vital omission, and that is no losses. And I'll say yet, because we will take those losses into account later. So for this problem, absolutely continuity must be maintained. And for this one, momentum must be maintained. So if I take a control volume here, and I say to myself, I'll make the control volume here. Make this the control volume. Here's my control volume. And along this total top edge, there's no mass out, so therefore we're all good. Key is the ground retarding this motion enough to be in some of the forces in the X direction? Are these large enough? And then the second question is, are they known in any meaningful fashion, in any way? And the fact of the matter is, they're kind of not. So if I look at the equation, first of all, this attaches itself to that. So B dot N and area, and that's essentially it. So we're going to make the assumption here, and this is pretty standard assumption, is that these shear forces at the bottom retarding the motion of the fluid from left to right here are pretty much unknown. And then what we'll do is sum the forces, control surface. Now, what we're probably going to do is we're going to find something out that's a discrepancy here. Or what we'll do, maybe I'll do it this way. I'm going to take this and move it to the bottom. I'm also going to, and maybe I'll do it this way. Here. Move this down. And then above it, I'm going to basically do continuity. Control surface. V dot N A. Now, it's a good opportunity to do these by saying, okay, this term is emitted from here, and this term is not there. Both of these are equations that have to be met. Now, I'm going to, I know what I'll do. I'll do a left-right here. I'll take the continuity and sort of move it down into the left, and we'll take the momentum, put it right here, put the continuity, kind of put it over here, and then I'll split these two. Now, I'll start working on the left. And what we have here, what we have here, 0 is equal to, and I guess I need to designate this being 1 and this being 2, V1 x, V1 dot N1, and these are both vectors, A1 plus, V2x, V2 dot N2, A2. Now, assuming that they're constant on the back, as far as the depth into the page, I would have 0 is equal to V1x. It's completely in the x direction, so that's just going to be a plus 18. V1 dotted N1, okay? If you go up here, there's your velocity. But here's your N. Likewise, here's N2. Not to scale, obviously, because Because the length of N1, the length of all the ends is equal to 1. But what you get here is a dot product between these two that is negative. So you get a minus 18 times area 1. Well, the height is this times 1 into the board, so we're just going to call it 0.6 plus the exit 3.4 completely to the right, and this time v dot n, these two dots go the same direction, they become positive, and then the area 2 is just h. This means, move that over, 18 squared times 0.6 divided by 3.4 squared. $16.817. Now what I'm going to do something interesting here. Okay, so I need to remember this is page 276 right here. Okay, so let's look at this. Page 276 is where I want to go to, but I want to go find the answer. Oops, wrong place, wrong way. How about 760? Well, okay. Now I've got to remember the problem number that I had, 512. And looks like I have an error, 3.18. Let's see if we can find what the issue is. Well, what I did, hang on. What? I goofed up completely because in my brain I was including this, and in actuality it need to be there. I apologize about that, but I'm going to show you something interesting out of this. When I see these problems, that's what I immediately see. So that my brain was somewhere it shouldn't have been. I apologize. Let's go back here. And there you go. 3.17. Wait a minute. 65. That's what I get. He, on the other hand, oh, okay, 3.8. So, okay, that I apologize for. But the reason I looked at this problem initially and thought about it was I thought about the fact that he's not asking you, in order to get this solution, he's not asking you this, to use this. But if I did use this, what do you think these forces would look like? Okay, now, again, this is my mindset that when I started this problem, I immediately started thinking about a particular way, and I started thinking about these forces, and that's what led me to make this mistake of including this Vx. However, let's look at this from a momentum viewpoint. What is the implemented forces on the x direction? Well, now that I've got this answer, it's 3.1765. I'm going to copy this equation down into the right, and I'm going to recopy. Okay, the thing was I'm going to go 250. Is that it? I'm going to go back to the problem, take a couple of snapshots of the problem itself. I'm going to use it for the snapshots. Okay, here's the snapshot I'm going to try to take. Okay, here's my snapshot. I'm going to go over here now, and I'm going to look at something here, go further with this problem to find out some piece of information that I want to know. Okay, what do I want to know about this? If I look at this problem, the reason I did this is I want to put the forces on this one, and I want to put the velocities over here. So in light of that, what I'm going to do that's interesting. Oh, I'll just make new equal sign. Okay. So what are the forces on this? Okay, again, let me look at this from this point. I'm looking at the force back here. It turns out that if we look at the hydrostatic pressure, that's totally legitimate. And we could look at the hydrostatic pressure over on this side. I'm going to draw it over here because it looks a little bit better. So here's our forces in the x direction. Now I also have a shear force here. Now this force would be equal to the shear force, whatever it is, times the area down there. But I'm just going to look at it and call it the retarding force, or FR, what the force would be on the fluid in order to make this thing operate the way it is. From our previous thing, we found out H was 3.18, so we're going to use that in here. And if I look at this on the left-hand side, okay, this force is equal to F is equal to gamma H bar area, which I'm going to assume it to be water. H bar is the distance down to the centroid, which is 0.6 over 2. That's that. And the area is 0.6 by 1. Now, the F on this side, I'll call it 1. This, I'll call this 2. Is gamma H bar A. Different, same gamma, different H bar. Because now it's this distance down times the area of 3, which I wrote 2, that's the area. So in essence, I could say this, F1 minus F2, because this one's pointing this way, the F1's pointing that way. I'm going to say the retarding force. And I'm going to assume it to do this. Now what I'm going to do is I'm going to put in all this. Now here's what the beauty is I'm going to do this. I'm going to go back to this equation Now this is where I got myself in trouble there a minute ago. And you take this, sort of slightly line it up. I'm going to assume that I can do this, and I can. Let's see if I can do this. Okay, can't really do it. Now, this is just simply continuity times the velocity. Now, we'll do this again. Copy. And sort of drop it right there. I don't think I can do this way, but I almost did. 18, 3.4. Now, this is 3.18. So again, the same logic applies. This became negative because it's going in. This is simply the area. X component of velocity. X component positive because it's going out in the area. So I'm going to figure out the right hand side real quick. So 3.4 squared times 3.18 minus 18 squared times 0.6 gives me minus 157.64. Now what I'm going to do is I'm going to go back up here and calculate these values. Here we go. 52.4 times 0.6 divided by 2 times 0.6, 11.23, 2.